Welcome to Daily Papers, the podcast where we break down cutting-edge research into conversations you can actually understand.
Today, we're talking about a classic tech problem. You ask an AI, like ChatGPT, to write some code for you, and it looks great, until you find a tiny hidden bug that messes everything up.
Exactly. For most things, a small bug is an annoyance. But what if that code is running your car's brakes, or a satellite, or a life support machine? In those cases, the code can't just be mostly right. It has to be perfect, provably perfect.
And that's the huge challenge this paper tackles. It's called Proof2Silicon, prompt repair for verified code and hardware generation via reinforcement learning. It's from researchers at the University of Illinois Urbana-Champaign.
That is a mouthful. Let's break it down. What does it even mean for code to be provably perfect?
It's a concept called formal verification. Think of it like a mathematical proof for your code. Instead of just testing a few scenarios, you use logic to prove that your code will work correctly for all possible inputs, every single time. It's the gold standard for safety-critical systems.
Okay, I see why that's important, but large language models, or LLMs, are famous for making stuff up sometimes. How can you possibly get them to write code that passes such a strict mathematical test?
Well, that's the billion-dollar question. The first instinct might be to try and retrain a giant model like GPT-4 on tons of this formally verified code. But that's incredibly expensive and time-consuming. It's like trying to teach a brilliant creative writer to suddenly become a meticulous logical mathematician.
So what's the alternative?
This is where the paper gets really clever. Instead of trying to retrain the superstar LLM, they brought in a coach, a smaller specialized AI whose only job is to get better at writing the instructions or prompts that are given to the big LLM.
A prompt writing AI coach? I love that. How does the coach learn to be a better coach?
Through a process called reinforcement learning. It's basically a game of trial and error with rewards. The process looks like this. First, the small AI coach writes a prompt to generate some code. Second, the big, powerful LLM takes that prompt and writes the code in a special language called Daphne, which is designed for this kind of verification.
And then the third step must be checking the work.
Exactly. A verifier program automatically checks the code. If the code is perfect, the coach gets a big reward. Game over, you win. But if there's an error, and there usually is at first, the verifier sends back a detailed error report.
It's like a teacher marking up a homework assignment with red ink.
Precisely. The AI coach takes that feedback, the red ink, and learns from its mistake. It treats the error as a penalty or a negative reward. Then it tries again, writing a slightly different, hopefully better prompt. This loop repeats over and over, with the coach getting progressively smarter about what kinds of instructions lead to perfect code.
So it's not about making the LLM itself smarter, but about making the requests we give it smarter. That's a really interesting way to solve the problem.
It's incredibly efficient. They call this part of the system preface. It steers these powerful but sometimes unreliable LLMs towards generating code that is 100% correct, without ever needing to change the LLM itself.
Okay, so that's the proof part of the title. We've got provably correct software, but the paper is called Proof2Silicon. Where do computer chips come into this?
This is where they take it to the next level. Getting verified software is amazing, but designing hardware, the physical circuits on a chip, is another incredibly complex and error-prone process. The researchers said, what if we could automate that too?
So they want to go from a simple English sentence all the way to a blueprint for a physical chip. That sounds like science fiction.
It does, but they built a pipeline to do it. It works like a series of translations. Once the preface system generates a piece of verified code in that Daphne language, the Proof2Silicon pipeline kicks in. First, it automatically translates that Daphne code into a more common language, Python.
Okay, that makes sense. A translation step.
Then it translates that Python code into a special high-level version of C code. This isn't just any C code, it's specifically designed to describe hardware operations. It's called HLSC, which stands for High-Level Synthesis.
So you're gradually moving from an abstract idea to something that looks more and more like a physical circuit diagram.
Exactly. The final step is to feed this HLSC code into standard off-the-shelf industry tools. These tools do the last translation, turning the C code into what's called RTL, or Registered Transfer Level Language. And RTL is essentially the detailed blueprint that you can send to a factory to manufacture a computer chip.
That is incredible. So you can start with an idea like, I need a circuit that calculates the absolute value of a number, and this system will automatically generate a formally verified, ready-to-manufacture design for it.
That's the promise, and their results are very strong. They tested this on a benchmark of 100 different tasks. The AI coach system, Preface, boosted the success rate of getting verified code by up to 21% compared to just using a standard prompt.
And how many of those correct programs actually made it all the way to a chip design?
A surprisingly high number. In the best cases, they successfully synthesized or created hardware designs for over 72% of the verified programs. They went all the way from a natural language request to a verified silicon blueprint.
So what's the big takeaway for us? Why is this so important?
It's about creating a foundation of trust for AI-driven engineering. As we rely more on AI to build the world around us, we need to be absolutely certain that what it builds is safe and reliable. This paper shows a concrete path for doing that in one of the most critical areas, hardware design.
It truly bridges the gap between a simple human thought and a complex, provably correct piece of technology. You're not just hoping the AI got it right, you have a mathematical guarantee.
Exactly. It's a pipeline that turns a conversation into a reliable circuit. It's a step towards making AI not just a creative assistant, but a truly trustworthy engineering partner for our most important systems.
That's all the time we have for today. A big thank you to the researchers for their fascinating work. Join us next time on Daily Papers.